try not to go too long, although I know I have too much stuff. After you've seen the preview of what's waiting for you outside under the clear skies, and I saw that, Saturn setting at 9, and I don't think I'm going to let you out in time to see that, unfortunately. So let's start exploring planets far, far away. But not with the Millennium Falcon, without hyperdrive. We're going to do it a somewhat less science fiction-y way, although what we're doing is actually catching up with science fiction. So here's an astronaut that all of you know.
Yes. Sing David Bowie.
And here's a virtual astronaut. I'm going to tell you how I and my students and my team explore distant worlds without ever leaving the surface of this planet, but using tools which are out in space, but not that much further than Chris Hadfield or other astronauts on the International Space Station have gotten away from the surface of the Earth. Here I am posing with an alien, and I just couldn't resist a little aside, is that there's been some speculation that aliens may have been visiting the lower mainland in the Vancouver area recently. And here is the news report on Fox.
Returning today, fans of a baseball game in Canada spotted what looks like a UFO. A local newspaper called it a cosmic intervention because after it appeared, the home team went on to win the game. Experts say it was probably just a light-up kite or something more mysterious like a small drone. Well,
so here is the video that went viral from that Daily Stadium. And the Canadians did win the game that night. Well, I'm here to confess that that was a hoax perpetrated by the H.R. MacMillan Space Center to promote our new digital projection system, the full dome digital projector that we have in the dome. And so it was a drone, a helicopter drone that was modified to look like the dome of the Space Center. By the way, the dome of the Space Center was designed to look like a Haida or Salish hat. So that's the shape there. And this was very difficult to do because the shape distorts the airflow from this helicopter drone. And so we had to bring in actually a Hollywood props expert to help us pull this off along with this marketing agency. And here's our teaser video once we confess to the hoax. So the question I heard is the Zeiss projector still there? That's Harold, as he's affectionately known. Yes, the Zeiss projector is still there in his bay and will rise out of the bay to take a bow. So he's in semi-retirement. He is still functional, about one of the last of the original types of Zeiss mechanical projectors that are functional. So we haven't. We're too fond of him to put him completely out to pasture, but he takes only a small part in the shows. And I can guarantee you, if you have a chance to come out and visit the Space Center and the planetarium, that our new full dome digital projection system will really blow you away. In addition to all the things that we could do before, you can fly through the galaxy, you can basically, and have lots of interaction in terms of interactive control with the audience. And we're putting on a show a little more down to earth, taking images to recreate Vancouver throughout its history. And you'll have full 360-degree, hemispherical panoramas of different places today and in the past in Vancouver. And we'll be unveiling that show in November, I believe. So to do come over and check it out. Well, talking about aliens and space travel, but let me now do time travel. I want to take you back in time to the night of the 7th of January, 1610.
I remember it well.
I remember it well. And at that time, there were only 6 planets known to all of humanity. The 5 that you could see looking up without a telescope: Mercury, Venus, Mars, Jupiter, and Saturn. All here in this real image, by the way, taken in Ontario. And the one that you could see without a telescope by looking down, the one we're on, the Earth. Now, the reason I picked this particular date in history is because this was the night that Galileo Galilei used one of his small telescopes to look at a wandering star called Jupiter, and realized that it wasn't just a pinpoint of light. It wasn't just a star. It was a world. It was a globe. And it had worlds whirling around it. It had moons looking like tiny stars lined up, seeing their orbits on the side. And night after night, he would observe what he saw through the telescope and sketch it. This is essentially Galileo's 17th century version of a science fair project. And it was these observations of a planet with moons going around it, not going around us, and not going around the sun, for that matter, that basically helped put the final nails in the coffin of the idea that the Earth was at the center of the universe. This was essentially the beginning of the age of telescopes. And over the next centuries, telescopes got bigger, more sensitive, the optics improved, and at the focus, instead of putting eyes there, eventually we put photographic emulsions, and then eventually digital detectors like CCDs. And in about 392 years of effort, with better and bigger telescopes and more sensitive detectors, we added to the inventory of known planets by 3. And to be honest, we actually only added to it by 2 because we nasty astronomers demoted Pluto. We downsized Pluto. It's a victim of downsizing to the status of dwarf planet a few years ago. Let me tell you where we are as of this afternoon. 21 years after this. 941 confirmed planets and almost 3,600 candidates, of which I would estimate 90% will stand the test of time as we investigate them. What you see here is sort of a map of our local neighborhood in our city of stars, the Milky Way galaxy. I'll come back to that idea a little later. The sun is at the center of this map, not because we're at the center of anything, but because all the measurements we make of distance and so on are there. So that's a kind of a sensible place to put it. And the scale on this map is 50 light years, which happens to be the distance to another sun-like star, which was one of the first recognized to have a planet orbiting around it outside of our solar system. And this is meant to be kind of a 3D perspective, not quite Avatar 3D, although I will be talking about Avatar later tonight. In the days when there were only 9 planets or 6 planets, and before there were computers, if you wanted to keep track of the way that the planets orbited around the sun and the way that the moons orbited around the planets, for the ones that were known at the time, you used a mechanism, a clockwork mechanism called an orrery, named after some dead British dude, the Duke of Orrery. And these are real examples of them, and they could be hand cranked, and eventually they were motorized. That just won't cut it today in the modern era. Let me show you the modern orrery. So each one of these bullseyes, these circles, are the orbits of planets. At the center of each of those bullseyes would be a star, not showing the stars because it would just get too cluttered. The sizes of these circles, each of them represents a planet, and those are the relative sizes of those planets. And they're all orbiting at their relative periods. The thing what we've done is sped up time. You can see the days flashing by in seconds. We can zoom in on some of the more recently discovered multiple planet systems. And they're getting very sleepy. I worry about putting people to sleep during my talk. This probably doesn't help. But you can see these are multiple planet systems. And when I talk about the techniques that we use, we can detect many planets orbiting looking for things far, far away, not too surprisingly, the first things you find are the biggest ones, the most obvious. And that was true for the search for planets around other stars. The first ones we found were ones that were like Jupiter, the most massive planet in our own solar system, the king of the planets in some sense. It's about 11 times the diameter of the Earth and about 380 times the mass of the Earth. And here are examples. The colors are meaningless. That's just artist's conception. It's the sizes here, showing some of the large, giant planets that were found. But as we continued the search, as our techniques became more sensitive, and as we covered a longer and longer period of time, then we started to find smaller and smaller worlds.
What's
RE?
RE?
Radius of the Earth.
Oh.
So somebody's asking, what's R sub E? That's radius of the Earth. So Jupiter is 11.2 times the radius or the diameter of the Earth, and these are just those values. And so you can see that we're starting to get down to things that were roughly the size of the Earth. And then, basically, a couple of years ago, we announced for the first time the discovery of planets around another star that were the size of the Earth and even slightly smaller than the Earth. Here are real images of Venus and Earth. This is Venus in ultraviolet light. The Earth is seen from space. And Kepler 20e and 20f shown to scale. Again, the details on the surfaces of these planets are just total fancy. The size is the only information that's relevant here. And then, about a year ago, a team led by my former student, Jason Rowe, who's now a member of the NASA Kepler team, discovered a planet around another star that's about the size of the Earth's moon, smaller than the planet Mercury. So that's Kepler 37b compared to, say, Kepler 20f. Now you can see that we're not particularly good at naming planets. We're not allowed to. But while I'm talking about planet names, you saw something about the September skies. Well, later on, as we go into the winter, you'll start to be able to see Orion the Hunter, that constellation. And in the shoulder of Orion, the bright red star there, is the star Betelgeuse. And the name Betelgeuse comes actually from the ancient Arabic, Yad al-Jawza. Now you can kind of see where the el-Juz, Betelgeuse comes al-Jawza, but where does the Yad turn into B? Well, I'll get to that, but let me point out that the names of all the bright stars, almost all of the bright stars in our night sky, actually come from ancient Arabic. It's because it was Arabic astronomers who rescued the knowledge of Greek astronomy. The burning of the Great Library at Alexandria, that knowledge would have been lost, but they rescued it, took it back, and translated it into Arabic, into Farsi, and other languages, and kept building on it. And then centuries later, during what we call, what we call the Dark Ages, that knowledge was returned to sort of the Western civilization and translated back into Latin and French and German and eventually English, except the star names, basically they kind of kept as versions of the Arabic. And Betelgeuse is actually a mistranslation, because Beit al-Jawza they thought meant armpit of the giant, which is sort of where it is in Orion the Hunter. But the true translation of armpit would be this, and I can't pronounce it very well, but so this was a mistake, but it was kind of a nice mistake that we've lived with. I'm convinced I'm talking about planets far, far away, and when we're looking at the names of these constellations, I'm convinced that George Lucas is familiar with this, the origins of this, because he named one of the villains Jabba the Hutt. And the ancient Arabic name of the star Beta Piscis Australis may have been Jabhat al-Hut, forehead of the fish. So,
that looks like
it.
That is a forehead.
Anyway,
what is the closest star to Earth, and how far away is it?
The question is, what's the closest star to Earth and how far away is it? Well, the closest star to Earth is the Sun, and it's 150 million kilometers away. The next closest star to the Earth and the closest star to the Sun is Proxima Centauri at about 4.2 light years away, where every light year is about 19 trillion kilometers. So here are Kepler 37b and Kepler 20f, not very good names, but we are finding many, many new planets, even if we can't christen them with clever names. Now, one question that I pose is, why look? Should we look for other planets? Should anybody be spending their time on it? And when I ask that question to people, why look? There are two common answers. One is to look to see if there are places where aliens are living, and that is a sort of thing. And the other is to basically find an escape route in case we screw up this place. and Stephen Hawking has actually made that argument, but Stephen Hawking is dead wrong, because our ability to travel interstellar distances and the potential advances in that kind of technology are so slow compared to the urgency with which we need to face things here on this planet, environmentally, culturally, politically, and so on, that this is not an escape route. But there is an environmental justification for looking for and studying these other planets, because they can teach us more about this planet, the Earth. And I'll try to give you a few examples of how they can give us insight, teach us some lessons about our home world. Because if you really want to understand the Earth, you've got to have other examples. If you want to understand the Earth in context. The question is, how do you find other examples? How do you find what an astronomer would call an exoplanet? That's our term for any planet orbiting any star other than the Sun. Well, the most obvious thing, we've seen some beautiful examples of astrophotography this evening, is why don't we just take a picture of another Earth around another star? We've got honking big telescopes, we've got sensitive digital detectors. The problem is that planets are faint. I showed you this image earlier. We have a front row seat to our own solar system, and yet without telescopes, without binoculars, we can only see 5 other planets. When the Voyager 1 space probe, which, at least according to NASA, last year finally left the solar system, crossing the boundary of the boundary of the way the sun's magnetic field interacts with the rest of space, it looked back from a distance only 20 times further from the sun than we are, and it took this snapshot of us. This is something that Carl Sagan nicknamed the pale blue dot. Now, 300 billion kilometers sounds like a big distance. It is to you and me in terms of human scale. It's nothing in terms of astronomical distance. We, in our galactic city, 300 billion kilometers, we haven't not only left the neighborhood, we haven't even left our own house. So this is a very close distance. Imagine now trying to see that Earth from a distance 1.5 billion times, 1,500 million times further away around a nearby star. Now, if you want to do it, to try to explain why planets are faint, lighthouses are bright if you're close enough to one. They're certainly bright compared to flashlights. So take a look at a lighthouse. You're staring right down the beacon of a lighthouse. Think of it as a distant sun. Think of it as another star that's harboring an Earth. This sun from afar, just like this lighthouse beacon, is about 1 billion times, 1,000 million times brighter than any Earth hiding in its glare, or any flashlight that the lighthouse keeper might have left on in the beacon. The only reason we know the flashlight is there is because we turned off the lighthouse beacon. We can't turn off stars. Probably a good thing. So if we want to take a picture of an Earth orbiting another star, we don't have that capability yet of being able to distinguish the Earth, even as a dot, against the glare of its parent sun. So it takes me back to my question. Okay, taking pictures isn't the way to go. How do you find an exoplanet? Well, to explain that, I've got to talk a little bit of physics, but don't worry, I'm not going to use any equations. The idea is that stars and planets aren't nailed down in space. They're not tacked down into space. And the reason the Earth is orbiting around the sun is due to gravity. But gravity is a mutual force, a mutual attractive force between two bodies. So the sun is tugging on the Earth and forcing it to move in this big orbit, but the Earth is also tugging on the sun. Now the sun is 300,000 times more massive than the Earth. And so it doesn't get the sun to move very much, but it does get the sun to move. As the Earth orbits the sun has to move in response to that mutual force, in reflex. And so it's not so much like physics as like dance. Stars and planets are round, they're spherical, they orbit in mathematical shapes called ellipses that sometimes can be a perfect circle, but their motions together are more like a pair of square dancers. And let me illustrate that with some examples of some dancers. Showing you this because what we're seeing are kind of analogies for the way stars orbit around each other and the way planets orbit around stars. These two girls dancing, their arms locked together, are doing the force of gravity, keeping them locked in orbit around one another. They have the same weight, and so they're spinning around a point directly between them, just like two stars of the same mass. The boy and his little sister, the boy is slightly heavier than his sister, so as they spin around, he makes a slightly smaller loop than his sister does, just like one star which is more massive than the other. And here, the dad is way heavier than the baby, that's the technical term for it, way heavier, just like the star, which is way more massive than a planet orbiting around it. So the dad only has to sort of wobble around a little bit, while his son goes around in this wide orbit, and a star like the sun has to make just a tiny little wobble in its dance compared to the sweep of the planets orbiting around it. That balance point in the orbits we call the center of mass, which is much closer to the star's center because it's so much more massive than the planet. And here's just a little cartoon, not to scale, to show you that balance point. So basically, stars are forced to wobble around as they dance. And before I go, let's have a round of applause for the band, Finger Dan and the Modal Nose. Right from the Cantina, Mos Eisley, and the planet Tatooine. So that's how we detected the first exoplanets, because the star has an unseen dance companion which is forcing it to wobble around slightly with the same period as the unseen planet. Now, how do we measure that wobble? Well, the answer to that question is the same as how does a speeder get a ticket? And it's due to something called the Doppler effect. Now, if you've got something that's giving off waves, it doesn't matter what kind of wave. It can be sound waves like you're hearing coming from me right now. It can be light waves. It can be ripples in water waves. But if whatever's giving off the waves is not moving and is sort of symmetric, the waves radiate outward in all directions equally. Here you're seeing it two-dimensionally, but it can be coming in and out of the screen as well. But if that source of waves is moving towards you, then the wave crests bunch up. And if you measure the distance between the wave crests, the wavelength, what you measure is shorter than what's actually coming from the source of the waves. And if it's moving away from you, then the waves lag behind one another and you measure a longer wavelength than what's actually coming. And that also can translate into frequency. If we were talking about sound, we'd be talking about the pitch of the sound changing. And if it's moving at some angle, as long as it's not a right angle across your field of view, you will measure some shift due to the component of the motion which is directly towards you or directly away from you. If we're talking about sound waves and the thing is traveling at the speed of sound, we call that speed Mach 1, and notice how all the waves pile up on top of one another. They create what's called a shock front, and that's what's responsible for a sonic boom. You can't just hear it. You don't just hear a sonic boom. You can see a sonic boom. Here's a photograph of a jet as it's passing through the speed of sound. But here, I can do that one better. Here's a video of a jet going faster than the speed of sound. And what you're seeing there are clouds forming around the nose of the jet that are tracing that shock wave front. Because what the shock wave is doing is it's causing the moisture in the air, the water vapor, to condense. And if you have condensed water vapor, you have clouds. Except not a puffy cumulus cloud, you have a conical cloud which is tracing out the wave fronts of the sound waves all piled up on top of one another to create a shock front. If you've seen the movie Man of Steel, the latest Superman movie that was shot in Vancouver, my friend Mackenzie Gray plays one of the evil Kryptonians in it. There is a scene where Superman jumps away from the Earth and flies away and goes through the sound barrier. And if you watch the movie carefully, you will see as he goes through the speed of sound, you will see a conical cloud forming around his torso. I was very impressed. Now, if the thing's traveling faster than the speed of sound, it's supersonic. Nothing we know of could go faster than the speed of light and be superluminal except Superman and the Millennium Falcon, but up to now, it looks like Albert Einstein was right about that, and here he is hitching a ride for the Millennium Falcon, but we'll see what happens in the future. But right now, there's a speed limit of 299,792 kilometers per second, not per hour, per second. So if you want to drive to another star, you got to go, and you can't go any faster than that speed. And as somebody asked earlier about what's the next star next to the sun, in kilometers, 40 trillion kilometers. And even at 1 billion kilometers per hour, that takes a while. And this is a zero tolerance speed limit. You know, there are no exceptions to go over that. And so that's the reason why I'm saying we're not looking for other planets around other stars to look for places that we can escape to, because we just aren't anywhere close to the technology of being able to escape there. Not one person, not 7 billion of us. So here's the kind of cartoon you'd see in a high school or an introductory university textbook to illustrate the Doppler effect. I don't know if that makes it any clearer than what I did. But a Doppler effect is how in modern days a speeder gets a ticket. Because what we call a radar gun is essentially a radio transmitter and a receiver. It sends out a radio wave of a known wavelength, a known frequency. And then some of that wave bounces off of the bumper of, say, an approaching car. And some of it's reflected back and picked up by the receiver. The receiver measures the wavelength of the frequency of the echo, compares it to the wavelength of the radio wave that was sent out, and the difference between, you use a Doppler effect equation to figure out what's the speed of the approaching bumper. And if it measures 75 kilometers per hour in a 50 kilometer per hour zone, you're going to get a ticket. So basically what we've done is we have radar guns for stars, except that we don't have to bounce anything off of them. They give off their own light. This little incandescent bulb in the cartoon is meant to represent the light from a star. We capture it with the telescope, focus it, and pass it through an instrument called a spectrograph, and we obtain a spectrum, a rainbow of the starlight. And here is the spectrum of the sun. You see the familiar colors of the rainbow, the kind of light we see by eye. You also see a bunch of stuff that looks like cracks in the picture, and these are the fingerprints of the elements in the gas in the sun. It's like a barcode for the sun. And if you scan that barcode correctly, you can figure out what the product, what the sun is like. And that's what we do. But we can also use these fingerprints. Their wavelengths are known. We can use them as a ruler to measure what are the wavelengths. And then if we see a star that has a planetary companion in a dance, in an orbital dance, this is what's happening. We don't get to see that. We don't even get to see the star wobbling back and forth like here, even though you can't see the planet. But what we can see is in the rainbow, in the spectrum, we can see those parts of the barcode shifting back and forth due to the Doppler effect. And we translate those into the motion, the apparent motion of the star, and we see it going up and down again. And the time that it takes to repeat is the orbit of the unseen planet. The size of this shift tells us some limit on the mass of the planet. And the shape of this curve, in this case a sine wave, tells us the shape of the orbit. I can tell that this is a planet in a circular orbit. And if it were not a circular orbit, this would have a more sort of like a sawtooth edge shape. And so that's the technique that led to the discovery of the earliest planets and still the majority of the confirmed planets. And it's a Canadian idea. And here are the pioneers. My friend and colleague, now retired, Gordon Walker, was at UBC, Bruce Campbell, who was a young astronomer at UVic at the time. And they were the ones that got it all started. They began the first search for planets, the first real search for planets. And in fact, as it turns out, they did discover the first planet, but they were cautious scientists, and they kind of put a question mark and said, well, maybe there might be some other explanation for it. And they just gone forward and said, we discovered the first planet around another star. The textbooks would read slightly differently. But the one that you will see in the textbooks, and that I marked, used for the scale of that little neighborhood of the sun map that I showed near the beginning, were these two guys, friends of mine from Geneva, Michel Mayor, and it was his student at the time, Didier Callot, who used the technique developed right here in British Columbia to find a planet around the star 51 Pegasi, a sun-like star in the direction of the constellation Pegasus. Now this planet was a bit of a surprise. Something that's like Jupiter in terms of its size and its mass, but 20 times closer to its sun than we are to our own. Jupiter is 5 times further from the sun than we are in our solar system. It became nicknamed a hot Jupiter. And when I tell my students about this, they're skeptical because I've taught them about the characteristics of our own solar system. And this is a quote from one of my students last term: "No way that can be a real planet, a gas giant so close to its star." That's the way I felt when this was first announced. And scientists were justifiably skeptical, but we found more and more examples of them. And it turns out nature surprised us, is that the planets around other stars and the characteristics of other solar systems are very different than our own solar system in many cases. So here's just an assortment. Again, the colors are irrelevant, just showing planets that are larger than Jupiter, and then going down in size. There's Neptune horning its way in to show a scale of the ice giants, and getting down to the size of the Earth. And what we're learning is, as we study other solar systems, is that in terms of our own solar system, how it came to be and how it's evolved, way more complicated than we used to think even a few years ago. It turns out if you want to make a solar system, you got to break a few more eggs than we used to think before. We are literally rewriting the textbooks. Some of the things I'm telling you tonight, some of the things I tell my students, my astronomy courses at UBC this year, 5 years ago, wasn't even on the table, on our radar. We didn't even have the language for it. And it's a very exciting time. If you're going to rewrite the textbooks, you need something to rewrite them with, a pen. I have several pens, and here are my pens. And my pens are satellites, and these pens draw what we call light curves, a record of the brightnesses of stars and planets as a function of time. Except above the turbulence of the Earth's atmosphere that makes stars twinkle, and from perspectives where we can stare at stars for months or years without interruption, we can make the most precise measurements of the brightnesses of stars and how they change ever in the history of science. And the first one to do this, the pioneer, was Canada's first space telescope, designed, built, and operated at UBC under my supervision, called MOST. Now, when you think space telescopes, most people think of this one, rightfully so, Hubble Space Telescope, an incredibly successful and versatile orbiting observatory. That's America's space telescope. Let me show you Canada's space telescope side by side. There it is. Now, MOST stands for Microvariability and Oscillations of Stars. Microvariabilité, Oscillations Stellaire, perfect Canadian acronym. Probably why we were funded by the Canadian government. That's why I came up with it. But because of this comparison with the Hubble Space Telescope, we nicknamed MOST the Humble Space Telescope. And since we were launched, people recognized that we had stolen elements of the design from a famous Hollywood celebrity, and so we are sometimes legally obligated to call it Space Telescope SquarePants. SpongeBob has become our unofficial mascot. Now, as I said, what MOST does is measures light curves. It's a light meter, like you'd have on a digital camera, except that it's not beside the camera, it's at the focus of the camera, at the focus of a specially designed telescope that's in a specially designed satellite in a specially chosen orbit. And here I am in the clean room with MOST before we launched it. I'm in my bunny suit here, and MOST is capable of seeing variations in starlight for certain stars as small as 1 part in a million, 1/10,000th of a percent. Even astrophysicists have a hard time wrapping their head around variations in brightness that small. And if astrophysicists do, you can bet that government bureaucrats in Ottawa that you're approaching for funding do. So I had to come up with a way to explain this so that non-rocket scientists could appreciate it. How sensitive is it to see a drop in brightness of 1 part per million? Well, imagine going to New York City and looking at the Empire State Building at night. All of the office lights are on, all of the office window shades are completely open. You could make the Empire State Building fainter by 1 part in a million, by 1/10,000th of a percent, by having one person stand at one window and pull down one window shade by 3 centimeters. And if you had that person move that window shade up and down by 3 centimeters, about an inch, you would make the Empire State Building oscillate like a star with an amplitude of 1 part per million. And that's what MOST is capable of measuring in stars, and we've exceeded that, and we were the first in history to be able to do that. So that's the first space telescope, and we were launched now over 10 years ago, June 30th. This year was our 10th birthday, launched from a military cosmodrome in northern Russia. And we were supposed to be a 1-year mission to observe 10 stars. We are now over 10 years old with more than 5,000 stars under our belt. Now, so we were launched on the 30th of June 2003, 10 years ago. Following us into space a few years later was a French mission called COROT, Convection, Rotation, and Transit. So you got to work really hard on acronyms sometimes. But unfortunately, the French mission failed last November when the instrument and its onboard computer stopped talking to one another, and the French Space Agency a few months ago finally gave up and shut down the mission. A few years after that, the Americans finally got into the act with Kepler. The official term isn't big sat, but if MOST is a microsat and COROT is a small sat, then Kepler is a big sat, over 5 metric tons. Launched the day after my birthday in 2009. But unfortunately, in May, the second of 2 of its 4 reaction wheels, which enable it to point, failed. Now, here's one of the 4 reaction wheels that's in this part of the spacecraft. They're like gyroscopes that control the momentum of the satellite and allow it to point and keep pointing despite all the things that will cause a space telescope to drift or to be tugged away from it. Now everything else, and I'm on the executive council for Kepler, in charge of it, and we are now soliciting missions to work with only the 2 reaction wheels. Not as good pointing, but there's still science that we can do. Otherwise, the rest of the spacecraft is functioning beautifully, and it's basically like having a Lamborghini, having a finely tuned sports car in which everything is working perfectly except the steering wheel. And so, who would have guessed that after 10 years, in which these satellites with much bigger budgets, COROT's budget $350 million, Kepler $1 billion, MOST $10 million, that we'd be the ones still running. And we are running with the big dogs. And the big dogs have gotten tired. We're still yapping away. Now, I am part of the COROT team and the Kepler team, so it's not an S&M thing here, but it is surprising and satisfying. We built SpongeBob to be a hardy little baby. Now, even though the Kepler satellite stopped collecting its original type of data in May of this year, that doesn't mean the mission's over. There are 2 years of it observed for 4 years, and 2 years of those data we are processing and haven't released publicly. There are hundreds and there are thousands of discoveries waiting to be found in those data. So the satellite, even if the satellite were dead, the mission goes on. And so I want to tell you, rather than bragging about my baby, about most, let me tell you a little bit about Kepler, because I play a major role in that, and as I mentioned before, one of my former students is a key member of the Kepler team. So what the Kepler mission is, it's another one of these light meters, photometers, monitoring about 160,000 stars for what turned out to be 4 years, with enough precision to detect planets the size of the Earth and smaller in what we call the habitable zone. And I'll come back to what we mean. Just to give you a sense of scale, by the way, there's a technician in his bunny suit posing beside the satellite. So it's a big sat. It has a primary mirror. You saw, you had a chance to look at some pictures here, although you can't see the telescope, but you heard a little bit about the center's new telescope, which has a primary mirror that's about 40 centimeters, I guess?
14.
No,
14 inches. 14 inches, yeah.
Yeah, 14 inches, which would be about in the 40 centimeters ballpark. So this is 140 centimeters, but it has a lens in front of it and so on. Its effective collecting area is like a mirror that's just under a meter across. It left our Earth to search for other Earths the day after my birthday in 2009. Here's the launch. Here's watching the launch trail in a longer exposure. By the way, it looks like the thing is plunging back to Earth, but spoiler, the Earth is round, and so if you launch things, eventually they're going to go below the horizon, even though they're heading safely into orbit. But not into orbit around the Earth, into orbit around the Sun, in an orbit very much like ours, but trailing behind us. And data were transmitted to Earth every month. You had to point the satellite so that the antenna could send the data. After 1 year, we were trailing around by a little bit. After 4 years, we were trailing by a lot. And that was also a factor that would limit the mission life, because eventually it would get so far from the Earth that there wouldn't be enough strength in the transmitters to get the data to us. The eyes of Kepler, the telescope, is focusing the light onto an array of 42 CCDs. And here's one of them, again, in the clean room, and there's the whole mosaic in the clean room. Total of 95 million pixels, 94.6 megapixels. Now, if you go to a store to buy a camera today, a digital camera, 16 megapixels is considered reasonably good and impressive. So we've got about 5 times, more than 5 times that, actually about 6 times that. And, of course, these cameras aren't designed to take pictures of aliens, or at least places where aliens might live. We're searching for planets in the sky. Here's a picture of the sky showing the constellation Aquila, the eagle. Do you see an eagle there? I don't see an eagle there. This is what an eagle looks like to me. If I see a bird there, I pretty much see an angry bird. That I can see. But this isn't the part of the sky that we were searching with Kepler. This is the part of the sky that we were searching with Kepler. On the edge of the constellation Cygnus, the swan. Okay, the swan, I don't know, I don't even see an angry swan there. But hey, that's what it's called. It is supposed to be a swan in flight overhead. So this is the tail of the swan, the wingspan, and the head at the end of the long neck. And you saw earlier so the summer triangle, still with us tonight, the star Deneb at the tail of the swan is one of the 3 stars in the summer triangle, and there's Vega, one of the others. And this checkerboard pattern is basically the part of the sky sampled by that mosaic of CCDs in the Kepler camera. Well, searching for planets in the sky is like looking for needles in a haystack. And what we're actually looking for are transits of planets. Now, if you say the word transit to most people, they think public transportation system. You say transit to me or to an astronomer, and they will more often than not think planetary detection system. So let me explain what I mean by transit by starting with something a little more familiar in concept, and that's an eclipse. So when there's a total solar eclipse, the moon, which is much smaller than the sun but much closer to us, is able to block out the bright disk of the sun and allow us to see that pearly glow of the corona, the base of the solar wind. A transit is when something passes in front of a star, like the sun, But it's not big enough, it's not close enough that it blocks out the whole disk. It just takes out a little chunk. And each one of these is a time-lapse series. Now in our solar system, there are only 2 planets that can transit as seen from the Earth, and that's Mercury and Venus, because you've got to be between us and the Sun, and those are the only 2 planets that go between us and the Sun. Most recent transit to Mercury occurred in 1999, 2003. That's Mercury, by the way, its shadow blown up there. That's a sunspot. That's like acne on the Sun, like a zit, which is actually bigger than the projected silhouette of Mercury. And here, these are real images taken from a NASA satellite in the ultraviolet. And that's why it looks blue, because you can't see light in the ultraviolet, so we can make it whatever color we want. But the relative intensities, the brightnesses here, are the true fluxes seen in the ultraviolet. And hey, you know, it's a solid body. It blocks out light at all wavelengths. Now, Venus, the first transit of Venus in modern times occurred on the 8th of June, 2004. But the one before that, 1882. So on the 7th of June 2004, there was not a single human being alive who had ever seen a transit of Venus with his or her own eyes. I was in England in a small town called Muchhool, which is near Preston, which itself is near Manchester, central Lancashire. Jeremiah Horrocks was the first human being to actually observe a transit of Venus from his bedroom in Muchhool. And astronomers from around the world and media from around the world had gathered there to sort of celebrate this transit opportunity. The night before, you know, on 7th of June, I was in a pub in Preston, and a young lady caught my eye, and I went up to the bar, started chatting with her, and then later went to her table. And as it was last call at the pub, I said, you know, if you come with me tonight, tomorrow I'll be able to show you something that no living human being has seen. It was a very good line. Anita and I dated for 2 years, and we're still very good friends. So you never know where you're going to use your knowledge of astrophysics. Well, the last transit of Venus occurred on the 5th of June, 2012, and it was observed by the NASA's Solar Dynamics Observatory. And this might put me behind time, but this is so beautiful. It takes about 3 minutes. I think you'll appreciate this. So those of you that did witness the transit, those of you that photographed it, but here is a time lapse sped up in time of the transit, seen first in the light we see by eye, and then seen at different wavelengths of light when the sun itself looks like an alien star. And again, Venus is a solid planet, so it blocks out light no matter what wavelength. And in all of these wavelengths, we're seeing its silhouette. In the optical, what we see by eye, and there are those zits I was talking about. And you can see the turbulence in the solar atmosphere, what we call granulation. And now, looking at the chromospheric activity, at I think this might be H alpha. I didn't do my homework, so I'm not sure which all of the wavelengths it's on. And all of this is real. I mean, again, we can't see these wavelengths by eye, so we've had to apply false color. But the intensities of the colors are telling you the intensities of the emission in different parts of the sun. You're seeing the activity, you're seeing when the flares are going to be born, you're seeing when the sunspot groups exist.
Good measure of time too.
Yeah. And there Venus takes its
6 hours or something.
Yeah. So here it is flashing through the different wavelengths of the instruments on board the Solar Dynamics Observatory. There you can see the magnetic fields of the sun being traced out by charged particles and prominences. Remember, this is our closest star and our most familiar one, but see it this way.
You can see it's the sun's rotation too.
Yeah. And now Venus makes its final bow for this transit.
100 more
And
years.
this was provided by the Goddard of the Space Flight Center. We give them their credit. Well, when I said that was the final bow, of course that's not the last transit of Venus, but it's the last one for a while. The next one won't happen until December 2117. So if you miss the last two, you got to be very patient. Well, in our solar system from the Earth, of course, we can only see transits of Mercury and Venus. But if you're beyond the orbits of other planets, if there are alien astronomers out there and they were looking at our system, they could see Jupiter pass in front of the Sun, covering about 1% of the disk, and the Earth passing in front of the Sun, covering only 1/100%, 1/10,000th of the area of the Sun's disk. Well, we are alien astronomers, at least if we're looking at other planets around other stars, and we can make those kinds of measurements. So here is showing an animation with time sped up of a planet orbiting around a star like the Sun. What you're seeing here is the planet is going through phases like the Moon does, and we can't see this, but we can measure the brightness of the star, and when the planet passes in front of the star, it causes the light to dip. And when the planet passes behind the star, we lose a little bit of the light from the planet itself, but not very much. It's kind of like the amount of light that you would lose when a mosquito buzzes behind a street lamp. And you're looking at the street lamp and the mosquito from a distance of 1,000 kilometers away. So if you have a sensitive enough light meter, you can measure these things, and you can even measure that little dip when the planet light, the reflected light from the planet, is cut off. And my student Jason, working with me several years ago for his PhD, was the first person to make this kind of measurement, to measure the albedo, the reflectivity of an alien world. And these transits are the only ways we can actually measure the size of a planet, its actual diameter relative to the diameter of the Sun, of the star that it's orbiting around. And that's what tells us, combined with that Doppler wobble technique, the Canadian technique, it tells us the true mass of the planet. So this is one-stop shopping. If you want to study an alien system, if it's transiting, you can learn the most that you can learn for any system, and that's why they're so exciting to us. Here I showed you an example of a transit measured with MOST. Here are 5 transits for 5 different stars measured by Kepler, showing the stars and the planets, their relative sizes and their orbital periods. Now what we're doing this because we want to understand stars and planets, and to put our own Sun and our own world, Earth, in context. To understand the stars and the planets you're seeing here, the Milky Way, 2 satellite galaxies, the Large and Small Magellanic Cloud, the stars in our galaxy. This was taken, by the way, in a quiver tree forest in Namibia, in Africa. To understand those stars and planets, some of the philosophy is the same as to understand the humans who live on this planet and who live in Namibia near that quiver tree forest. One thing, you need to have a large sample. If you really want to understand human beings, you want to pull a large sample. A very large sample. A humongously large sample. So when it comes to human beings, you might want to go to a city. Well, that's what we want to find. We want to find a city. Here's a city. I played the Cantina Band music from Mos Eisley Spaceport, but not a very big city. Here's a bigger and a real city. Happens to be Edmonton. We need a large city, but we need a large city at night. Okay, here's Edmonton, seen at night. We need a large city in the clouds, in the sky. There's Bespin, Cloud City from Empire Strikes Back. We need a large city in the clouds, though, at night. Okay, at night. Well, we have that. And here it is, with amateur astronomers having a star party in the foreground. You're seeing that in the background. The Milky Way galaxy. Here's what the Milky Way would look like if you could see it from outside. Here's another spiral galaxy similar to our own Milky Way. And this is basically a city of stars. a city with a population of several hundred billion, of which our sun is just one stellar citizen. It has city limits so vast that light would take 1,200 centuries to go from one edge to the other. And we don't live in the downtown core, we live out in the suburbs. So if this were, metropolitan Vancouver, we're the Surrey of metropolitan Vancouver. And here's how it would look from the outside. So with Kepler, we're staring into our galactic city in this direction with that little checkerboard pattern, looking at about 160,000 stars in that direction, looking for these periodic dips in brightness as the planets pass in front of their parent stars. This is the volume of space. Here's a perspective view of our Milky Way galaxy. And basically we're searching, it's kind of like a rectangular cone, 3,000 light years long in our neighborhood. Now there's more than 160,000 stars in this cone, in this volume of space. We picked the stars that optimized our chances for detecting planets. And why 160,000? Well, it's because the orbits of planets can be randomly oriented from one star to the next. And so if you just look at one star, the odds are, even if it has planets, those planets aren't going to be in orbit that's lined up along your line of sight, so you're going to see transits. So you got to look at a lot of stars in order for the statistics to work with you, so that out of 160,000 stars, you can find hundreds or thousands of planets. Now, I talked about the population of our galactic city in terms of our sun being one member of that city, and it's a G-type star. The letters here are what we call spectral types that we use to sort stars by temperature. So these are the coolest, these M's, and the O's are the hottest and the largest. And the sun is a G-type star. But these massive hot stars are rare. And these very low mass cool stars are the most common. And in our galactic city, about 70% of the population are these M-dwarf stars. These tiny stars, tiny dim stars. You want to judge a star by its size? Judge me by my size, do you?
Look at me. Judge me by my size, do you? And where you should not. For my eye is the force, and the powerful it is.
Well, Yoda has the right idea that we shouldn't judge things by their size, but in this case, we should, except we're making a favorable judgment. When you're looking for exoplanets around stars, small is good. M-dwarfs, here is what would happen if the Earth was passing in front of a star like the Sun in our solar system, making a very, very shallow dip in the transit. Very, very challenging to measure, even with Kepler. But hey, an M-dwarf is only a third the diameter of the Sun, only a tenth of the area of the Sun. And so a planet the size of the Earth takes out a bigger chunk of it and makes a bigger dip. And it goes around that star more often, and 70% of the stars in our galactic city are this kind of star. So the odds are, if you're going to find planets, and planets in the habitable zone, as I'll talk about in a moment, it's going to be around this kind of star. So size does matter, and M-dwarfs are very important. Now when I keep talking about habitable zone, looking for life, question of life out there, some people might think of it as a rerun of a Fringe episode, or the X-Files, which just celebrated its 20th anniversary earlier this week, or a fairy tale. And it is actually a fairy tale, but in a good way. But not the fairy tale quite of Goldilocks and the Three Bears. It's more like Jaymie and the Three Planets. Let me come back to our own solar system to illustrate this. The Sun and the planet Venus. Venus is the Earth's sister world. It's almost the same size, almost the same mass. It has a thick atmosphere. For a long time, scientists were convinced that Venus was a place where you would find life beneath the clouds. We now know that Venus is a hellish place with a surface temperature of 500 degrees Celsius, hotter than the melting temperature of lead, and due to a runaway greenhouse effect in its atmosphere. And so, for life as we know it, it's too hot. Mars. Mars has had all the good PR. If you think of alien life, often you think Martians. And it does have an atmosphere, a thin atmosphere. It does have water, frozen in the polar caps and the permafrost. But it's not exactly a tropical paradise for vacation. The atmospheric pressure at the surface of Mars is less than you would breathe at the top of Mount Everest. It's mostly carbon dioxide. And it's called the average temperature on Mars, 60 degrees below zero. And so for life as we know it, at least complex life and liquid oceans of water, it's too cold. And then nestled between Venus and Mars is the Earth. Average temperature on the surface 15 Celsius. And as we know, for life as we know it, Earth is just right. It's in the zone. The zone, what we call the habitable zone, sometimes nicknamed the Goldilocks zone, because if you're too close, it's too hot. If you're too far away, it's too cold. And if you're in the zone, this bowl of porridge is just right. And it's basically a range of distances from the star in which the surface temperature would be between the boiling point of water and the freezing point of water. So you can have liquid oceans. It's kind of like being around a stellar campfire. If you're too close, you're too hot. If you're too far away, you're chilly. The right distance, you're comfortable. But not all stars are campfires. Remember, 70% of the stars are these M dwarfs. They're kind of like kindling, stellar matches. So the habitable zone, the Goldilocks zone, is much, much closer to the star. But that's a good thing for us, because that means that a planet in that zone would orbit around the star much faster than a planet the distance of the Earth. And so in our data, we have many more chances to see a transit and to build up a better signal. So here's just a cartoon around a star like the Sun. The green zone is the habitable zone, the Goldilocks zone. Hotter stars, it would be further out. Cooler stars, it would be closer in. There aren't a lot of those, and there are many, many of those. And with Kepler, we did find a planet a couple of times the diameter of the Earth. We announced first a couple of years ago, Kepler 22 system, in which this planet's just in the inner edge of the habitable zone. And so what we're looking for are Earth-sized planets in that Goldilocks zone. I said that we call these planets around other stars exoplanets, and here's an artist's conception of one of those systems that we found. Anybody else, though, would call them alien worlds. Alien worlds like Tatooine. Here's a scene from Star Wars, not a documentary, fictional film, spoiler alert, orbiting a binary star system. We used to think that that was unrealistic for dynamical reasons. Nature and Kepler proved us wrong. This is also an artist's conception, but not of a fictional system, of a real system. We have found planets that are orbiting binary stars, and we call them the Tatooine systems. Kepler 47. So you would literally see a double sunset. And if you could see the planet transiting its pair of stars, here it is. In this one case, it's a sun-like star and one of those M dwarf stars. And there's the silhouette of the planet. This is also an artist's conception, of course. Alien worlds like Pandora, James Cameron's conception in Avatar. And here is a scene from Avatar on the surface of Pandora. And I can tell you unequivocally, based on the preliminary results in our search for planets around other stars, that Pandora is absolutely boring. Boring. Let me tell you about an exciting planet. HD 80606b. James Cameron would come up with a more exciting name for it than that. It's orbiting one of these two stars that are almost 60 light years away from us. Both stars are like the sun, and to see them, you'd look in the direction of the sky where you'd see the Big Dipper. Put things in perspective, let me just show you. Here's the sun and the Earth's orbit, nearly circular, takes a year to go around the sun, 365 and a quarter days. Here's the orbit of HD 80606b. This wonky thing shown with the sizes of the orbits of Mercury, Venus, and the Earth. And so it's in this very elongated elliptical oval orbit. It goes out almost as far as we are from our sun, but then it swoops in over the surface of its parent star every 112 days. We zoom in on the inner part of this orbit when it would come in closer than Mercury is to the sun in our solar system. Each of these symbols is a day apart. Each of those dots is a tenth of a day, 2.4 hours apart. Orbital mechanics say that when something is closer to its star, it's moving faster. That's the way it works. And so the distance from the star, here we're talking about a week to go from the distance of Mercury to almost on top of the star. The amount of light that it gets from its parent star changes on a matter of hours. And the whole planet's weather changes in a matter of hours. Now, I'm not talking about the weather here, like in the Sunshine Coast, going from clear to cloudy to rainy and back to clear again in a few hours. I'm talking about the weather everywhere in the entire world, changing in the same way at the same time on a time scale of a few hours. We're concerned about climate change. We're so worried about the fact that the evidence shows that the average temperature has risen by 1 or 2 degrees Celsius in the past century and maybe continuing to go up. That's nothing. Think about HD 80606b, where models suggest the temperature can go up by 400 degrees Celsius in a week, and then drop by 400 degrees the next week. I call it a climate roller coaster. Science fiction writers didn't even imagine a planet like this could exist. If you got to George Lucas when he was working on Star Wars and said, "Hey George, you should put in this planet that's like this climate roller coaster where the temperature goes up and down by 400 degrees in over 2 weeks," he would have rejected it as too outlandish. And this is the guy who came up with Jar Jar Binks. So we're really outpacing the science fiction. Here's the weather forecast, by the way, on this planet. High temperature today of 1400 degrees Celsius, kind of toasty. Very windy, but it's clear. And speaking of George Lucas, here's the weather forecast on Alderaan a long time ago. The galaxy far, far away. On Monday, it was partly cloudy and a high temperature of 72 degrees Fahrenheit. Tuesday, sunny, 74 degrees Fahrenheit. Wednesday, 15,000 degrees Fahrenheit. And then Thursday and Friday, there was just no weather forecast. This nasty Death Star thing. Here are models that we have generated in conjunction with NASA. There's orbiting Spitzer Infrared Observatory and using most data of the weather on this exoplanet. And compared to this, Pandora is conventional. Earth-sized world with normal gravity. Well, it does have unobtainium, which floats against gravity, and it's got big blue creatures with tails. But as a planet, it's fairly conventional. It's actually not a planet, it's a moon. It orbits around a gas giant, which you can see in the background in the shot. Well, speaking of Avatar, Avatar 2 is shooting still. It's behind schedule. And you can ask, where will Avatar 2 be set? Well, to answer that question, first let me show you a picture, a cartoon from the Probe 7, the BC grade 7 science textbook, showing roughly the inner structure of the Earth. We have discovered planets that we call super-Earths that are several times the mass, several times the diameter of the Earth. And some of them have the same kind of internal structure, just different proportions. And I should point out that of these planets getting down to the size of the Earth, and here's a plot, and we're going in the radius of the Earth up to 5 times the radius of the Earth, the mass of the Earth, in terms of the mass of the Earth, up to about 18 times the mass of the Earth. And these curves represent different models of planets dominated by iron, planets dominated by rock, planets with a very thick layer of water, ocean. And these dots represent known planets with their measured sizes and masses, and the reason why they're crosses, these represent the uncertainties. So, the actual values could fall anywhere within that kind of cross. There are 17 of these for which other beyond the planets that are in our own solar system, for which we know the mass and sizes, out of the hundreds that we've confirmed and out of the thousands of candidates. And in this plot, the ones that you're seeing highlighted in red are based on most measurements, Canada Space Telescope measurements. And look at the sizes of the crosses. Look at the error bars here compared to what you're seeing around, with a few exceptions. We know the parameters of these two planets better than we know the parameters of any other planet outside of our solar system. The rest are due to the NASA Kepler mission and the French Corot mission. 17, and we've got 2 of them at a cost of $10 million. So, and again, I have to remind you we are running with the big dogs, and again, I have to remind you we're still running. And so, you know, this is a big deal. So a lot of what you're finding, these are the poster children for planets to study. And the ones that kind of look like the Earth on the inside, in terms of the way we would model them, we might call Terra super-Earths. But there are also ones that we would call aqua or ocean super-Earths that have incredibly deep oceans. You saw those models that said 50% water. These models were first developed by an expat Canadian, Diana Valencia, of Argentinian heritage, who was a student at the University of Toronto, did her PhD at Harvard, and is now a Carl Sagan Fellow with NASA.
I don't get something. You have a solid iron inner core and a solid water inner core in this planet. How is that
That's not an inner core, that's a solid water mantle, that's ice.
That's what I mean.
Yeah.
How can you have ice underneath liquid water?
Because it's a special, ice has different crystalline forms that are called isomorphs, but in this case it's isomorphs. If you ever read Kurt Vonnegut, Kurt Vonnegut had a novel called Cat's Cradle, in which scientists at Los Alamos developed Ice 9, an isomorph. There is an Ice 9, but not the one that's in Cat's Cradle, which freezes at above room temperature. And so basically the crystal, a little of this Ice 9 gets out and basically freezes the entire world. Spoiler alert if you haven't read the book. But there are real isomorphs, and it's like the triple point. It's a function of the temperature, the pressure, the density. And so there are certain isomorphs, these would be Ice 7 and Ice 10, which actually will freeze under these conditions where you can have ice beneath liquid water. And yeah, remember I said it sounds like the science is overtaking the science fiction. This sounds like science fiction, and a few years ago it was the kind of thing that you would have only read about in a Kurt Vonnegut novel, but now it's actually the kind of stuff that we're exploring.
And solid iron, similar?
Why not? No, it didn't say solid iron, it says iron core.
Yeah, but the previous
I didn't say
one
solid
said
iron.
that, said that the Earth had a solid iron core. The previous slide?
Yeah, the Earth does have, it basically, here where we go.
Solid iron inner core.
Yeah, we have a solid iron inner core and a liquid iron outer core. That's why we have a magnetic field. If we didn't have the liquid iron core, there wouldn't be a magnetic field.
The liquid or the solid?
Well, it's the boundary between the liquid and the solid. If we didn't have a solid inner core and a liquid outer core and a mantle on top of that, we wouldn't have the magnetic field.
Is the inner core hotter than the outer core?
Yep.
Wow.
Yep. But it's under higher pressure, higher density. Anyway, the reason I'm introducing these aqua super-Earths is just because, to answer the question, where will Avatar 2 be set? James Cameron has stated that the movie they're shooting, the Avatar, is set on an ocean super-Earth. He loves oceans. He loves underwater, Titanic, Abyss, and so like an aqua super-Earth is a James Cameron wet dream. It really is. Now, the reason I wanted to talk about these aqua super-Earths is to come back to this idea of putting our own Earth in perspective. Because we think of ourselves as living in a lush, wet place. We are on a planet in which 3/4 of the surface is covered by ocean. The volume of those oceans is about 1.4 billion cubic kilometers. Who thinks in cubic kilometers? I don't even think in cubic kilometers. But if you were to divide all of that water equally amongst the 7 billion human beings on Earth, then we should each get 200 million cubic meters of water. Except we're not the only living things on Earth. So if we shared it equally for every person, animal, and bird on Earth, it would turn out to be about 3,000 Olympic swimming pools each. But the amount that's accessible to us and that would be drinkable would actually be only 3 swimming pools each. And I forgot, plants and insects, they need water too. That distills it down to basically 1 swimming pool each. Now, it doesn't mean that this is, you go through this water supply and use it up, you can recycle it. But if everybody realized that if things were divided equally, and they're not, but if they were, that each of us should be allocated basically one swimming pool of water, and that's the supply of water that we will rely on for our lives for our entire life, then we probably would be less inclined to pee in that pool. It would teach us to be better managers of water, of ocean resources, and so on. And so, as we find these other planets and see these other environments, it can put our environment in a sharp perspective. Because we think that we live in a very wet, lush place, but compared to the volume of ocean in an aqua super Earth, 700 times the volume of the Earth's oceans, we don't have oceans, we have puddles. And if there are aliens out there, and if aqua super Earths are common, they probably feel sorry for us. Earthlings planet covered in puddles. They call them oceans and they think they're really deep. Here's the real headline. Our galaxy is filled with alien worlds. We have been making the announcements and we will continue to make announcements. Our next conference in California will be in early November, so stay tuned for that. And if you read the fine print, soon someone will find an Earth-sized planet in the Goldilocks zone. And then on a time scale, I would say about between 10 and 20 years from now, somebody will be announcing evidence for life on one of those planets in the Goldilocks zone. Probably microbial life, but the signature of life forming on another planet. And to be honest, one of you, basically, you're about the right age. Any of you people, basically, if you decide to go on in science, it doesn't even have to be astrophysics, you might be the ones who are making a talk like this 20 years from now here to the, except that you'll be talking to the Nobel Prize Committee and so on, announcing the evidence for life on one of the planets. I and my students and my team members, my colleagues around the world, are finding the places where life might exist elsewhere, and to be able to focus the search. Jill Tarter, who used to be the head of SETI, Search for Extraterrestrial Intelligence. The movie Contact, Jodie Foster's character, is based on Jill Tarter. She stepped down from SETI and joined the Kepler team because she knows that we're finding the places where we want to focus the search. So, like I said, and by the way, if one of you do find, eventually find the proof of life elsewhere, when you giving your Nobel Prize acceptance speech, mention me. Just say, hey. I'd like to thank you for your patience tonight. This is one of the ads that Vancouver Science World ran last summer with basic ideas about science. It turns out, according to surveys, the most common fears that people have are clowns and heights. So here are clowns holding a net, inviting you to jump from a great height. My greatest fear is that I never leave time for questions, and I know that I've lived up to that fear. But in case you don't have time to stick around and ask any questions, feel free to contact the management, the executive of the Sunshine Coast RSC Center, and they can give you my contact information. And feel free to contact me with questions after tonight. Thank you again for your patience and your good.